Hey physics kids, this is Mr. Daniels over here. Hello CCARS kids. Today in this video what we're going to be doing is talking about free body diagrams and more importantly using free body diagrams to help us solve problems that involve Newton's second law. And Newton's second law, as you can see on the board up there, is the net force equals mass times acceleration. Let's go ahead and let's look at the step-by-step processes that we're going to be using here to solve these problems. We'll be going back and forth from this slide as we actually solve a problem, but the first thing, as you can see, that we need to do here to solve a problem with Newton's second law is draw a free body diagram of the object of the interest here. Here's our first sample problem. The maximum force a grocery bag can withstand without tearing is 200 newtons. If you loaded 15 kilograms of groceries into a bag and tried to lift it upward with an acceleration of 4 meters per second squared, would the bag tear? Okay. As we can see over here, first thing I do is draw our free body diagram. So step one, let's go ahead and let's just circle our object of interest, our grocery bag. Now, let's look at our contact forces. As we can see, the only contact force we have is right here, which is our hand. If we look, that's it. But we know that's not the only force we're dealing with here. We do have long-range forces, our long-range force, which is going to be gravity. Okay, so we can really take this picture and isolate what things are actually interacting with it. Our long-range force, gravity here, and our contact force of the hand here. Let's draw our free body diagram. We know that it has a mass of 15 kilograms. Okay? And we know that we have a downward force and an upward force. The upward force is the hand, the downward force is that long-range force of gravity here. And of course we got to label these forces. So let's go ahead and let's label the downward force, force of Earth on bag. And let's go ahead and let's label the upward force, force hand on bag. Okay, so looking at the interactions we have, we can see that those are the two forces here. The upward force, the force hand on bag. The downward force, the force of Earth on bag. Now, going back here, we can see we have to choose direction. Well, in this case, I'm going to say that this is our negative direction here, and this is our positive direction. So we're saying going down is negative, and going up is positive. Okay, so we said that we're making up the positive direction and down the negative direction. Now, from our diagrams, you can see in 3, we got to determine what the net force is. In this case, let's not look at numbers, and let's actually look at our equation here. We know Newton's second law says the net force equals mass times acceleration. So let's look back over here and look at that equation. Net force equals mass times acceleration. In the case of this example right here, we're going to say that the force of the hand on bag, I just simplified hand on bag to H on B over there, minus the force of Earth on bag, once again simplify that, equals mass times acceleration. So just taking mass times acceleration, put it there, and just expanding this net force to mean the force of the hand on bag minus the force of the Earth on bag. So that's the equation we're looking at here. Now, let's go ahead and let's substitute here. Let's actually plug some numbers in here. Let's substitute our net force and actually start doing some algebra here to solve. Now we know, according to the problem, that our acceleration is 4 meters per second squared. Our groceries are 15 kilograms. Let's go ahead and let's solve these, or substitute these numbers in. don't know the force of the hand on bag. That's what we're trying to figure out here. We're trying to figure out if the upward force is more than 200 newtons right here, then our bag is going to break. So we don't know that. That's what we're actually trying to solve for here. Force of earth on bag. Well, we know the force of earth on bag is caused by gravity. We know the mass of our object is 15. Gravity is negative 9.8 meters per second squared. If we go ahead and do the quick calculation right there, we can see that the force of the earth on bag is negative 147 newtons. So this right here, force of earth on bag, equals negative 147 newtons. And I can change colors to make things a little more easy. Equals, our mass is 15. Okay, 15 kilogram bag of groceries here. And then our acceleration is 4 meters per second squared. So we get the equation, the unknown force of the hand in the bag minus a negative 147 equals 15 times 4. We know 15 times 4 is going to be 60, so we can go ahead and say that the force of the hand on bag minus negative 147 equals 60. We can go ahead and get that force of hand on bag by itself. To do that, it's going to simply add 147 to both sides. We know that 60 plus 147 is going to be 270 newtons. If we're going to look back at our answer here, this is the force that the hand is applying to the bag. We know that the bag breaks at 200 newtons. So what we can see here is that we know that if we have more than 200 newtons of force, the bag breaks, and then we can see that we do have a force of the hand on the bag of 207 newtons. And I just realized my mistake here. This should be a plus negative 147. The math is correct. I just messed up my sign right there. I apologize for that. But we do know that 60 plus 147 is going to be 207 newtons. 207 newtons is greater than the 200 newtons breaking limit of the bag, so the bag does break here. All right, here is another example of solving Newton's second law problems with free body diagrams. What we have here is a sailboarder, and he is sailboarding in the Columbia River. And we know that the wind is blowing the sail to the right, 350 newtons of force, and there's 350 newtons of force that are causing drag between the board and the water. What we want to know is what is the acceleration of this sailboarder. Just like the previous example, let's go ahead and let's circle our object here to figure out what we have as contact forces. So if we go ahead and circle it, we can see that we have a couple things in contact. First off, let's tackle that long-range force. We know that we're going to have a long-range force that is going to be gravity here. Okay, so that's one of our forces. Now, we also know that we have the wind. We can see that the wind is blowing this sail to the right, so we have that contact force, which is going to be wind. So that's 2. And then we have to deal with the other contact force, which is the water. And in this case here, the water is doing 2 things. Right? So we have the water not only holding him up, but also causing drag. So the water is producing drag and holding him up. So those are our 4 forces that we're dealing with. So once again, let's go ahead, let's draw our free body diagram here. 100 kilograms is our mass. It says it right there. Now we know that we're going to have a downward force, and we'll label this one as force of earth on sailboarder. So force earth on sailboarder. And if we do the math real quick, we know that the force of the earth on sailboarder, 100 times gravity, which is 9.8, we get a value of 980 newtons. Since we did the downward force, let's go ahead and let's actually make this negative here. Since we did the downward force, Let's do this upward force as well. We'll label this one as the force of water on the sailboarder. And we'll give this a force of positive 180 newtons. Let's look at the other forces. We have wind and we have drag. Now it says that the wind is blowing to the right at 350 newtons. We can see that right here. So the force of wind on the sailboarder is 350 newtons. That's positive. Other force we're going to have here is the drag. Drag is going this way. So the force, as we can see right here, of drag, so we'll do force of water on the sailboarder, because this water is what's causing the drag there, is going to be negative 300 newtons. So as you can see, I gave positive and negatives to the direction. I made positive 350 to the right, negative 300 going towards the left here. Now, before we go any further, let's look at our upward and downward forces. We can see right away, positive 980 plus our negative 980 is going to be 0. These two cancel each other out. So really, we're just left with 300, negative 300 to the left, and positive 350 to the right here. What we can do is then take this and actually plug it into Newton's second law equation. We know that the net force is mass times acceleration. We know the mass. We're looking for the acceleration. We can find the net force. We can find the net force by just taking the right, positive 350, and subtracting it from the left. Equals our mass of 100 kilograms times the acceleration. Let's go ahead, let's fix that right now. We can tell that positive 350 plus negative 300 is going to give us a net force of positive 50 equals 100 times our unknown A. Very simple algebra here will tell us that our acceleration is going to be 0.5 meters per second squared. Since it's positive, we are going to the right, so if we want to put an arrow, we can go ahead and put an arrow direction right there.